Hi guys, and welcome back to Chem-MrT with me, Mr. T, and we're going to be carrying on with topic 1 today, looking at halogen displacement reactions, moving on from the halogens which we did last lesson. And this is again GCSE 1 to 9 chemistry, so it's both chemistry, the triple chemistry and the combined chemistry. So if you're doing the award where you're going to get 2 GCSEs, or the award where you're going to get separate GCSEs for chemistry, physics and biology, this is for both of those. And it's from topic 1, the atomic structure and periodic table, and it's from part 2 of this, which is the periodic table. So we're going to be learning about the order of reactivity in halogens. We're going to be able to predict outcomes of halogen displacement reactions, say what they are, and explain why this pattern of reactivity in the halogens exists. So firstly, the reactions of the halogens. Very simple. Just like group 1 elements, there is still a trend of reactivity in the halogens in group 7. It's slightly different though. Unlike in group 1, where the reactivity increases as we go down, in group 7, the most reactive halogen is fluorine, which is at the top of the group. And the halogens gradually get less reactive as we go down the group. So it's the opposite way around from group 1. And you can think about this, they're on opposite sides of the periodic table, therefore their reactivities are different. So here are the halogens. We've got fluorine, chlorine, bromine, iodine, astatine, and you don't really need to know about these last two. The ones on the syllabus for GCSE are fluorine, chlorine, bromine and iodine. Okay, they're the big ones that we're going to focus on. And as we go down the group, they get more reactive. Okay, so most reactive at the top, least reactive at the bottom. Opposite way round from group 1, where you've got our least reactive at the top and our most reactive at the bottom. Okay, so you could imagine that if you could get hold of some francium and react it with fluorine, because they're really super reactive, that reaction might be really violent and quite exciting. So one other thing that we need to have another quick look at is that the atomic radius, or the size of the atom, gets larger as we go down the group. Okay, so fluorine has only got a radius of about 0.07 nanometers, whereas chlorine is a little bit bigger at 0.10 nanometers. Bromine is about 0.115, and then iodine is about 0.13 nanometers. Okay, so as we go down the group, the atoms get bigger, and this makes a difference to the reactivity. Because as we go down the group, they get bigger because we get more energy levels, we get more electron shells getting added on. So fluorine has got 2 electron shells, the chlorine has got 3, bromine has got 4, iodine has got 5. The extra electron shells that we add on mean that the outer shell gets further away from the nucleus, and we've got more shells in between the nucleus and the outer electron shell. So why do the halogens get more reactive as we go down the group? So as we know, halogens, because they're in group 7, have got 7 electrons in their outer shell. They want to gain 1 more electron to make a full and stable outer shell, and this makes them reactive because they've only got 1 to gain, and gaining 1 electron is much easier than gaining 2 or 3 electrons. So as we go down the group, the atoms get larger, as we said, and the outer shell gets further away from that positive nucleus. Okay, the nucleus is positive because we've got the protons in there, P for positive, P for protons, and the electrons, because they're negative, get attracted to the positive charge. This means the outer shell doesn't get as much attraction from the nucleus as we go down the group. So from fluorine to chlorine, we've had an extra electron shell. That outer shell now, the new outer shell, is further away from the nucleus, so it gets less attraction, less of a pull from the positive nucleus. And that means it's harder for it to attract an extra electron. So how reactive it is depends on how easy it is for the halogen to gain an electron. To gain an electron, it's got to be able to pull one in. As the outer shells get further away from the nucleus, further away from the positive charge, it's harder for them to gain that extra electron. There are also more shells in between the nucleus and the outer shell, and these shield the outer shell from the charge of the nucleus, a positive charge, because we've got lots of negative charge in between the positive charge of the nucleus and the new outer electron shell. It means that the outer electron shell has been shielded. Okay, it no longer feels as much of a pull because there's lots of negative charge in between it and the positive nucleus. Therefore, the reactivity goes down. They can't attract electrons as easily. So halogens also get larger down the group. Okay, so as we said here's a graphical representation. So we've got chlorine, relatively small, bromine, bigger, iodine, even bigger. Obviously these are not to scale, these are not really representative, it's just to show you the idea that the atoms are getting bigger as we go down the group. Now we need to be able to prove this trend in reactivity. And we can do that by investigating compounds of halogens called halides with elemental halogens, so that's things like just chlorine, bromine, iodine by itself. If they're in a compound, they've been reacted with something else. And a halide, that's just a technical name for a halogen that's formed an ion with another compound, another element. And we, for the experiment, the one you'd probably do in school, is using potassium halide. So for example, potassium chloride, potassium bromide, potassium iodide, they're the ones you'd probably use. So we've got one potassium, which is K, reacted with one halogen, so whatever that may be. So for example, potassium chloride would be K for potassium, Cl for chloride, KCl. What we get is something called a displacement reaction. In a displacement reaction, a more reactive element kicks out a less reactive one from a compound. Okay, so an example here would be if we go back to our previous look at the group 1 elements. If we take lithium, which is not very reactive for group 1, if we take lithium hydroxide, into the lithium hydroxide you drop some potassium, you should see a reaction, and what will happen is you will form potassium hydroxide and you'll get back the lithium metal. Okay, because the potassium's more reactive, it kicks out the lithium from the hydroxide and takes the hydroxide for itself. And what we would do normally is we'd do an experiment with a table similar to this. So the left hand column down here shows our potassium halides. We've got potassium chloride, potassium bromide, potassium iodide. The little AQ in brackets shows it's dissolved in water. The top row shows a halogen we're going to react it with, so we've got chlorine, bromine and iodine, and they're in their elemental form but dissolved in water. So can you predict which of these are going to react and which won't? So we've got chlorine with potassium bromide and potassium iodide, we've got bromine with potassium chloride and potassium iodide, and we've got iodine with potassium chloride and potassium bromide. What is going to react? What is not going to react? I want you to think about this. I want you to think about the fact that a more reactive element will displace a less reactive one from a compound. So have a look at the compounds here. Determine which is more reactive or less reactive out of Cl, Br and I. So chlorine, bromine and iodine, and the chlorine, bromine and iodine here. Okay, have a little go and have a little predict. We're going to have a look at these one by one now. So put the video on pause to give yourself the time to think about these. Really do it. Okay, having a think about it and getting it wrong is much better for your learning than just waiting for the answer. Okay, you're engaging your brain, you're starting to build those neural connections. So here's the results table in large. You'll notice as well that these ones are brown because there's no point reacting chlorine with potassium chloride because it won't do anything. Same with bromine and potassium bromide because the halogen is the same as the halide here. Okay, so it only works if these are different. So first of all, potassium chloride and bromine. Okay, what we get is no reaction. Okay, chlorine is more reactive than the bromine, so when we mix the bromine with the potassium chloride, the chloride holds on to the potassium very, very strongly and kicks the bromine out and says, nah, no chance, you're not taking this potassium away from me. And the next one is exactly the same. Again, chlorine is more reactive than iodine, so there's no reaction. The chlorine holds on to the potassium. There's absolutely no way, because iodine is significantly lower down on the reactivity series than chlorine, there's absolutely no way that the iodine is going to steal that potassium away from the chlorine. The chlorine is just way too strong and will not let it happen. So now we move down onto the next row. This time we're going to be looking at potassium bromide. Now this time we know that chlorine is more reactive than bromine, and the chlorine wants that potassium. So the chlorine here will displace the bromine. It's going to kick the bromine out, and we're going to make potassium chloride, KCl, and bromine. Okay, and the bromine will turn the liquid yellow. Okay, all these liquids start off colourless or more or less colourless, and when we get the reaction, the chlorine forces the bromine out of the potassium bromide, and the bromine will turn the water a slight yellow colour. However, there's no reaction between the potassium bromide and the iodine, because the bromine is more reactive than the iodine. The iodine cannot steal the potassium away, so there's no reaction. Now you might be able to work out now that iodine is less reactive than both chlorine and bromine, so we're going to see a reaction in both of these, and the reaction we would see is the liquid is going to turn brown, because that's the colour that iodine goes when you dissolve it in a liquid. So chlorine's more reactive. It's going to kick the iodine out away from the potassium and take the potassium for itself. So we're going to form KCl and iodine I2. Again, same for the bromine. The bromine is more reactive, and so it's going to displace, kick out the iodine from the potassium iodide to form potassium bromide, which is KBr, and the iodine I2. So this is proof of the differences in reactivity. The chlorine is the most reactive, so it reacts with both the potassium bromide and the potassium iodide to displace the other halide from the compound and form potassium chloride. However, when we've got potassium chloride, neither bromine or iodine is more reactive than it, so it cannot displace the chlorine from the potassium. Now we need to be able to turn these into simple equations. Okay, so all follow a rule if the reaction happens, and that rule, we're going to use these two symbols. We're going to use X to represent any halogen. For example, that might be fluorine, F, chlorine, Cl, or Br. And Z is going to be a more reactive halogen, so a halogen that is more reactive. So obviously there is nothing that is more reactive than fluorine in terms of a halogen, so therefore we're not going to get one of these reactions with fluorine. So if we have a compound K potassium, X, which is a halogen, plus Z, a more reactive halogen, what happens is the Z and the X swap places, and we can see that the little subscript numbers stay in the same place, so it's just the letters that swap places. So an example for the reaction between potassium bromide and chlorine, which is Cl2, we know that chlorine is more reactive. What we get is 2 KBr plus Cl2 makes 2 KCl plus Br2. The chlorine and the bromine have just swapped places in their reaction. Very, very easy. So you should be able to write simple equations for all the other reactions. Again, you just write out what the halide is that we start with, so the KBr, 2KBr or 2Ki, plus the halogen that we've got in, and then on the product side, if there's been a reaction, you just swap the positions of the two halogens. If there's no reaction, you can write out a simple equation if you want. For example, KCl plus Br2 makes KCl plus Br2. There's no reaction. Or you can just write KCl plus Br2, arrow, no reaction, or equals no reaction, because nothing happens, nothing changes. Okay, summary time. So the halogens have an order of reactivity, just like the group 1 elements. However, they are more reactive towards the top of the group and get less reactive going down, missing out an S there on the less. Oops. This is because the outer shell of electrons get further away from the positive charge of the nucleus, because the atoms are getting larger as we go down the group. This means that the outer shell electrons feel less of an attraction, and we can use displacement reactions to prove the order of reactivity. And a more reactive halogen will displace a less reactive halogen from our compound. Okay, hope you found the video useful. Please ask any questions in the comments, and I look forward to seeing you soon. Okay, take care guys, bye bye.